Hello, everyone. So today we're looking at the answer key to the review packet for Unit 8 Magnetism. One thing you'll notice about my answer key is I actually updated the quizzes partially through the unit. So if you go replay the quizzes, which I strongly suggest because you know I ask test level questions on those, if you go play the quizzes one more time, you'll see that I added 3 questions to the end of the Models of Magnetic Field quizzes and 3 questions to the end of the planetary magnetism / magnetic forces quiz in the middle of the unit. So go check that out. It's a good use of your time. Okay, that being said, another good use of your time would be to use these laws of magnetism to practice the direction rules for field, force, and Lenz's law. I also included the review equations that you might need to know for this unit. Notation wise, notice that this E over here for electromotive force will most likely in class use a big capital V for voltage. That's the new notation. Okay, so let's get to it. The north pole of the magnet is located at D because domains align to point from south to north. This must be some sort of magnetic material. I can tell because it has domains. Only iron, nickel, and cobalt have domains. Copper, however, is not magnetic, so therefore does not have domains. Now, iron is a magnetic material, meaning all chunks of iron have domains. But an iron skillet can't pick up a paperclip because the skillet's domains are not aligned. It might look like something where some point up and some point left and some point down and some point this way, but that overall the fields cancel. The skillet in this picture can't pick up a nearby paperclip because it doesn't have a net magnetic field itself until it is magnetized. Now, one big main idea for the unit is that all electricity creates magnetism. All electricity creates magnetism. Whether that electricity is completely forming a loop, whether it comes from a battery, even lightning when it comes down to Earth creates a magnetic field around it. Big idea of this unit, magnetic field is always created when electricity occurs. So let's say electricity is occurring and we have a current carrying wire shown to the right, that's this. The current is traveling into the page. That's what that X symbol means, is into the page. Now, we know that around a current carrying wire, that the magnetic field is going to form circles. Compasses lined up around this would line up in circles around this wire. And to figure out their direction, point your thumb in the direction of current, that's into the page, and your fingers will curl clockwise. Now, please notice for this that you should be able to, get rid of 2 out of 4 choices here. It doesn't make sense that the magnetic field is into or out of the page because we know that it's forming circular shapes. A compass placed right here would point up. A compass placed over here would point down and to the right. So it has to be some sort of circular direction, either clockwise or counterclockwise. Similarly, for number 7, I can completely rule out A and C as reasonable places where the South Pole might be located. In this case, I know that my thumb points north, so D must be the North Pole, meaning B must be the South Pole. This is an example of an electromagnet. An electromagnet creates a magnetic field from current, and we can make this stronger by changing the core, the number of coils, and the current. We can also make those coils close together to maximize that magnetic field. Essentially, what's going on here is as soon as the current turns on, the core, which is inside this cylinder here, has its domains line up. The domains will temporarily line up as long as the current is on, and then revert to their unorganized state as soon as the current is turned off. So, now we've got a current carrying wire. Current carrying wires are going to experience a magnetic force that's perpendicular to both current and field. One more time, that means current has to be perpendicular to field, has to be perpendicular to force. Since the y direction is already taken by current and the x direction is taken by B, that leaves only my into and out of the page direction. I can cross out those two immediately. So, pointing my thumb in the direction of current and my fingers in the direction of field, my palm would push this wire into the page. Once I get it down to just two possible choices, those right-hand rules become significantly more manageable. But hey, speaking of which, if current is perpendicular to field and force, well, that means I don't get a force unless current is perpendicular to field. A, B, and C don't make sense. For C, the wire has no current. That doesn't make sense because force comes from a current. So it's not C. But it's certainly not A or B either. In A, that's picturing a wire with current traveling in the same direction of field. That's not perpendicular. Whereas B, current is traveling in the direction opposite the field, and hey, that's not perpendicular either. So if current, field, and force have to be perpendicular, the only choice is D. For number 11, if I make the current double, that automatically is going to double the magnitude of the force, leaving only B and D as options. Since the direction of the current is switched, that changes the direction of magnetic force, so B. Now we're getting into induction. You'll notice that all of these other laws except for D are laws that are numerical laws. Coulomb's law is the law of attraction and repulsion between two charges. Faraday's law is the voltage induced because of a moving magnetic field or a moving coil. Ohm's law is the one where voltage and resistance are proportional to current. So it must be that Lenz's law states that a changing magnetic field always gives rise to a current whose magnetic field opposes the original change. Wordy, but true. So, keeping on line with induction. When a magnet is moved through a solenoid, it has kinetic energy, that's your moving part of your magnet, that changes to electricity here. So the electrical energy comes from the kinetic energy used to move the magnet. Now, in this case, the magnet is being pulled to the left. Let's say that induces a current I. If it's now moved more slowly, we can assume that there is less electricity, less magnitude, and now in the opposite direction. So less electricity, opposite direction, that looks like A. Finally, on the multiple choice. All of the following are examples of power plants that use generators except fuel cell. All these other ones either use falling water to turn a turbine, and as that turbine spins, It moves magnets and creates electricity. Or rising steam. We burn the nuclear fuel and we burn the natural gas to heat water. And the rising steam then spins a turbine to create electrical power. So in either case, hydroelectric, nuclear, and natural gas all use generators. They turn turbines to create electrical power. Fuel cells are not. Fuel cells actually just use regular chemical reactions. In fact, 3 things that don't use a generator that are considered power plants would be things like fuel cells, solar power, batteries. Those would be chemical or solar interactions that create electricity from different forms of energy, not from kinetic energy. You can check because hydroelectric, nuclear, and natural gas all involve kinetic energy of some sort of moving turbine. Oh my God, guys, I have never asked a matching question, and it turns out this one's really hard to get them to match up nicely. So my bad on that. So, a magnetic material that has most of its domains aligns is a permanent magnet. Other word for that would be ferromagnet. A magnetic field formed by electric current is an electromagnet. A material that has all its electron spins paired off so that the net magnetic field is 0. This one is not an actual vocab word in this unit. But what I want you to picture for a non-magnetic material is picture something like copper, something like carbon. If I were to draw a picture of its domains, there wouldn't be any, because for every up electron spin in that atom, there's automatically a down. They automatically cancel each other out. So this is your pretty much every single material except for iron, nickel, and cobalt. Okay? So, the process by which changing a magnetic field causes a voltage in a nearby wire. That's going to be electromagnetic induction, which you'll also hear me just call induction for short. We know a domain is a microscopic section within a material in which most of the electron spins are aligned. Keywords for domain are domains are microscopic. A material that has domains but not necessarily aligned would be a magnetic material. So that iron skillet that we talked about in an earlier problem would be a magnetic material, but would not necessarily be a magnet on its own. It has domains. Those are not aligned. All right, so let's draw magnetic fields. These are super easy. They go from north to south, so away from north poles, toward south poles, from north to south, away from north towards south. And what these field lines represent is the direction a compass would point if placed in its presence. A compass placed here would point straight left. A compass placed here would point straight right. Now, how to use these drawings? We can use them to figure out where north and south poles are, because the north pole will be where the magnetic field lines are pointing away. The south pole will be where the magnetic fields are pointing towards. The magnetic field is going to be strongest wherever the field lines are closest together. So these are 2 potential locations with a strong magnetic field. The domains on the inside of the magnet point from south to north. And since this is hard to see on your copy, this would be pointing to the right on the inside of this magnet. And because of how domains align, if you accidentally split a magnet in half, the polarity remains the same. Meaning, let's say this is your magnet. The north end is to the right because that's where your domains are pointing to, and the south end is to your left. But if you cut it in half, that creates a new north pole here because that's where the domains are pointing to, and a new south pole. Fun fact, this is why you can't have a magnetic monopole. If you keep trying to split this in half, you eventually get to a size where you can't cut this domain down any smaller without splitting atoms themselves. We can't split an electron in half, so we can't make a magnetic monopole. So this was the demo that I did in class. For this, we know the magnetic field causes compasses to align in circles around this wire. But we don't know in what direction. So then we're going to use a right-hand rule. Point your thumb in the direction of current. That's up and to the right. And this is one of the thumbs up right-hand rules. So your hand should look like this. With my fingers up and to the right, my thumb up and to the right, I see that the current is going in the counterclockwise direction, this way. So that compass, as a result of this magnetic field it's feeling, would align itself in the same direction as the field lines. In order to increase that field, I could increase the current. So I can increase I. That would make the compass align more. I could bring the compass closer. That would make it align more strongly. And we didn't really talk about what mu is. Mu is the magnetic material that is surrounding the wire. And sometimes we put a little 0 right here. If there's no material around the wire, then that's just some universal constant. I guess you could make it stronger by encasing the entire outside of this wire in iron, but that would also make it really hard to put a compass nearby. So we kind of ignore that possibility. More important to note, current goes up, field goes up. Closer you are, field is stronger. If the compass were placed really far from the wire though, let's say the compass was placed, I don't know, over here, far from the wire, it would experience much less field. So rather than lining up along this circular magnetic field lines, it would point to whatever direction magnetic south is on our planet. So, solenoids. We can figure out where the north and south pole of a solenoid is by taking our fingers in the direction of current. Whatever direction your thumb points, remember this is a thumbs up right-hand rule, is the north pole of the solenoid, making this a south. Similarly, the north pole is to the left, making this a south. If you're having trouble picturing where my fingers are curling, use your pen. Imagine I need to curl my fingers so that they go in front of this pen. Just like the lines are going in front of the solenoid. My thumb is on the right, so that's where the north is. Okay, so once I do this, the magnetic field lines line up just like regular bar magnets. They point towards south and away from north. And because the two south poles are near each other, they repel each other. And this can be made stronger by making either of the magnets stronger. I could change the core, the current, the number of coils, and I could make them closer together. So sometimes you'll hear me call these the 4 C's of electromagnetism. That's core, current, coils, closer. And if these were released from rest, imagine I'm going to draw them as bar magnets with the souths near each other. There would be some stored energy here. Whatever that stored potential energy is, would need to turn into kinetic energy after. And what do we call an energy that's stored in the location of an object? We would call this magnetic potential energy. This type of energy, maybe we would, I've never even thought of what we would call this for a symbol. or PEM, I guess. PEM, potential energy magnetic, would turn to kinetic energy after, because this is the energy stored in the field between them. Kind of like if we had a proton next to another proton, we would call that electrical potential energy. We would call this magnetic potential energy. Okay, so paleomagnetism. This picture shows that the magnetic field of the Earth changes back and forth. In order to calculate the speed, we would want to use distance over time. We're given the time in millions of years, but we're not given the distances. So we need a distance scale in order to solve this problem. For the next problem, magnetic force. This is the high five right-hand rule. For this, you would point your thumb in the direction of current, in your fingers in the direction of field. The field is out of the page. So I'm pointing my fingers up at this video. Oh, that looks weird. That's a weird view of my hand. But when I point my fingers out of the page and my thumb to the right, this would take that wire and push it down. So my force magnetic on wire 1 is down. My force magnetic on wire 2 is, oh gosh, uncomfortable, to the right. And just to double check, remember that current needs to be perpendicular to field and force. That means the force on I1 can either be up or down. The force on I2 can either be left or right, but we're only choosing between those two directions. Now, because current must be perpendicular to field in order to get a magnetic force, I need my current to go in the same direction of the field lines in order to make no magnetic force. So, in other words, if the field is out of the page, if I put current either into the page or out of the page, then we would have two quantities that are not perpendicular to each other. Picture in this case, because looking at this from above is a little bit hard to see. In this case, if your field were going in the positive x direction and your current were going in the negative x direction, that's not perpendicular, so that would make no magnetic force. If your field were going in the positive x direction and your current were going in the positive x direction, that's not perpendicular, that would have no magnetic force. So either draw yourself a current that's x's or a current that's dots, and neither of those would experience a magnetic force. In order to have this magnetic force calculated by ILB, I need to have the current perpendicular to field in order to create a magnetic force. But calculating it is easy. So 3 amps times 0.5 meters times 2 Tesla gives me a 3 Newton force. You can math this one out using acceleration as force over mass. That means rail 1, which has a mass of 0.5 and a force of 3 newtons, would have a 6 meters per second squared acceleration. But we can also just note that lighter things accelerate faster. Because of this equation, mass increasing should lower the acceleration. Heavy objects, less acceleration. For energy transformations then, these rails are objects that start from rest, and I'll actually just draw in a railgun. These are objects that start from rest with a big amount of current running through them, so electrical energy to start. And after a few seconds, or maybe if we're talking about the Navy railgun, not a few seconds at all, you have kinetic energy at the end. Electricity turns into magnetism, creates kinetic energy. This is the same energy transformation as a general motor. A motor in general turns electricity to kinetic energy. So for number 29, what would you need to do in order to induce a current in the coil? Well, if you remember from doing this lab in the class, what we need to do is move the magnet back and forth near this coil. It makes the most current if we make a stronger magnet, a faster magnet, bring it closer to the coil, even inside the coil would be good. We could also lower the resistance, because these three put together, I guess we can also change the number of coils, more current. These four put together then, these would increase the voltage, leading to more current, and lowering the resistance would also increase the current. So, as the north pole of the magnet moves into the coil, the flux should increase. Flux is the product of field times area, and the area is certainly not changing. But the closer it is to the coil means field is increased, and with more field, the stronger the magnetic flux. So in this case, magnetic flux is increasing. Now for the bar chart, this is kinetic energy that's turning into electrical energy. So all I'm looking for here for these bar charts then is to identify that energy transformation of the kinetic energy of the magnet turns into the electrical energy in the coil. So kinetic turns into electrical. This is typical of a generator. So there's a right-hand rule for field, a right-hand rule for force, and this one is the right-hand rule called Lenz's law for current. So the way to picture this one is for each of these scenarios, we need to determine if the flux is increasing like it was in C over here, decreasing, or remaining the same. You only get a voltage if it has a changing flux. That's what Faraday's law says. Faraday's law says that you get a voltage if the magnetic flux changes. So in this case, let's take a look at what happens with our original and our new coil. Let's say after a moment of traveling, the coil is now moved up. When it's moved up, that means flux has gotten larger. The area that's been enclosed by this coil is increased, so flux increased. Lenz's law says that if flux increases, then it induces a field in the opposite direction. And that's opposite to the direction shown. So the field was originally out of the page, therefore my new field must be into the page. So I'm going to draw the induced field in a completely different color, like red. So inside this coil, there must be a new induced field, one whose job it is to cancel out the increasing flux. Since flux is larger, this has to try and oppose it by putting it in the opposite direction. So finally, let's right-hand rule this. This is a thumbs up style right-hand rule. Point your thumb into the page and it sees your fingers curling naturally in the clockwise direction. So if there is a current induced in this wire, that current would go clockwise. And I say if there's a current induced because remember, this gives you a voltage. The changing flux in this case induces a voltage, and the current occurs if this is a closed path. If it's an open path, then you have voltage with no current, like a regular circuit whose switch is open. Okay, so let's do this one next, because here's an example where it does not create a voltage. Let's say this wire, one moment later, is in this new position. From the original to the new, it has the same amount of flux as before. The area enclosed is the same area. The field is the same field, and therefore, flux is some constant number. And since flux doesn't change, Faraday's law says no voltage, no current. Same for this one. Since it does not leave the field, one moment later, this box is here, flux is constant because the area enclosed in that field equation, so field times area, would be the same value. So again, voltage 0, current 0. Oh, I like that, that's easy. So finally, let's do a hard one again. As this is moving out of the field, it's now enclosing less area than it did before. In fact, if I draw it like this, when it leaves the field, it has some flux to start and 0 flux at the end. Flux decrease, and therefore, it was going to create a new induced field that's in the same direction as B. So the same direction as dots. The same direction as dots is dots. So my new field, which I'm going to draw in red, is induced to augment the decrease in field. So, in short, for Lenz's law says that the induced field is in the direction that prevents the change in flux. So if your flux is increasing, we want to oppose that by making a field in the opposite direction. If your flux is decreasing, we want to augment it and make it stronger. So we'll put a field in the same direction. Last step, right-hand rule. Thumb out of the page, fingers curl around, and that's going to be counterclockwise current. And that current will occur as long as there's a closed path in that wire. Which brings us to the last problem. So, magnetic flux, field times area. In this case, it's asking for when it is completely in the magnetic field. It has a field of 5, an area that's a rectangle, so 0.2 times 0.2 meters squared, and that gives us 5 Webers. Now, there's 2 ways to calculate induced voltage. Way number 1, we could calculate the change in flux. We would need to know the number of coils. If it doesn't say so, assume this is just one coil. But what I don't have when I look through this, I see these two together give me an area. We've got a velocity, a resistance, a field. We don't have a time, so I know right off the bat I cannot use this equation. So, other one. BLV. The field is 5 Tesla. The length is 0.2 meters. And just to be clear, the length I'm referring to is this one. It doesn't super matter in this case because it's a square. However, if this were non-symmetrical on all sides, I would need to make sure that I'm picking the correct L. Velocity is 5 meters per second. Oh, I totally mathed this wrong. Hold on. 5 times 0.2 times 0.2 is 0.2. Math in my head. 0.2 Webers. This one, on the other hand, that's 5 volts. That's what I was thinking. Okay. So I have a changing flux. I know that I do because as this moves into the direction of the field, this is increasing the area that's contained. It's going from half the area to the full area. Flux is increasing. So I am going to get a current. This is not a trick question. Lenz's law says that if the flux is increasing, then the new field is made in the direction that's opposite the original field. New field is opposite direction of x. What's the opposite direction of x? Well, that means the new field is dots. Dots are the opposite of x. So as this increasing flux is occurring, the new field is going to try and prevent that increase by canceling it out. So my new field is in green. I put my thumb out of the page, fingers curl around counterclockwise. If you're a person that wants to break this down step by step, what I do for Lenz's law is first I determine whether the flux is increasing or decreasing. Then, if flux is increasing, I know the new field is in the opposite direction of the original. Compare new to old. Figure out what direction the new field is then. Put your thumb in the direction of that field. So in this case, flux is increasing. Therefore, the new field is in the opposite direction of x. Since it's the opposite of x is dots, I put my thumb in the dots direction, the out of the page direction, and this goes counterclockwise. So, that leaves my last two questions. Current is voltage over resistance. We got 5 volts of induced EMF or induced voltage. Resistance is 4 ohms. That leaves 1.2 amps. 1.2 amps in the counterclockwise direction. After the loop is fully inside the field, voltage is 0. And to help you picture why that is, I'm going to draw on this picture again. Let's say it starts here, so it's fully inside. And 1 moment later, it's here. My flux before is still equal to the flux after. And so that means the flux does not change over time, so there is no voltage. Even though this equation would still work, please remember that this equation has a caveat. This equation is only good if you are either entering the field or exiting the field. If you are not entering or exiting the field, either use this one or no, it's 0. In this case, I can't use this equation as it's just moving inside the field, so look for the keyword inside the field here. So I know I can't use the enter-exit equation. And if I do this, I realize the flux doesn't change as it's inside the field. When I try to do flux before minus flux after divided by time, I'd get the same number, 0.2 minus 0.2 over whatever time. Doesn't actually matter what the time is because the voltage is 0. 0 over anything is still 0. Good luck!